Okay, I'm going to get started. This is about my adventures or misadventures with ARM encodings for the assembly instructions. It's a little bit about the tech, but more about the journey. So if anybody knows me, I've been doing ignorant stuff with x86 for a while. And in the back of my mind, I kind of want to experiment with ARM, but I didn't have, it was harder for me to emulate, and I didn't really have any ARM devices to be able to really play with because I wanted to work with bare metal. And then I realized for like years I've had a Raspberry Pi, so that was kind of my start into that. I didn't know exactly where to start with learning assembly for ARM because it seemed like there's less books out there for it. But I found on the Raspberry Pi forums, they were all kind of pointing to this one resource. It's a kind of an ebook or a website that had a book about programming for like assembly for ARM and specifically on the Raspberry Pi. So that sounded perfect. I started there, but the annoying thing is the guy, I thought most assembly books were bad, and I don't want to super criticize people that much. This guy knows what he's talking about, but the approach of teaching assembly by writing C and then compiling it and then disassembling it to try to illustrate assembly, I think is the worst possible way to teach a newcomer assembly. And I know this is an eye chart, I'm not really intending to zoom in, I'm just saying this is a screenshot of him writing a C program to implement the stack, to then compile it and then decompile it. It's just the most confusing way to try to teach. So I kind of skimmed the book, I didn't really read it that detailed, and I gave up on trying to read textbooks or any kind of books on ARM, and I knew what the real source of information was going to be. I already read the entire, all 3 volumes of the Intel manual, so I thought I'd find the ARM manual and read that thing as well. So I read that, and at this point I'm not even at Hello World, I just read the whole manual first. And I'm really getting hyper-focused on the machine encodings of the assembly instructions because that's what I do. In fact, by the end of this talk, when I even get to the main proof of concepts of everything I've done, even in the end of my research, at this point I still had not written Hello World because it's too high level. So this is just an example of an instruction, an assembly instruction for move, and in the bottom is kind of some ASCII text of how that's encoded in binary. So every ARM instruction being 32 bits for this 32-bit architecture, with exception to thumb instructions, which I didn't focus on. So you kind of see the fields broken out, like you have 4 bits for a condition, and you have some 1s and 0s that define that it's a move instruction. You have your register fields like RD and RM, and this is kind of the last we'll see of ASCII text, because then I'll get a little bit graphical after this, but this is how I was looking at them all. And the thing that immediately I thought was interesting about this instruction, and a lot of instructions related, is you see 1s and 0s, but you also see some 0s with parentheses around them. And the ARM manual is very, just architecture in general, is very organized, categorical, broken down really well. It explains what all those 1s and 0 fields are supposed to mean, except for those ones in parentheses. TLDR, they're don't care bits. But it doesn't go so far as to say they're don't care bits. It's not like I discovered this myself. It was pretty well known what those bits are already, but I didn't know. I wasn't in touch with the ARM community, so I hyper-focused on these don't care bits. I wanted to see what they actually did, if anything, and all that. But speaking of how I love the ARM architecture and how it's broken down, down the road I made this atlas, but I didn't have it while I was researching. But to show you, say there's a subcategory, a split, there's conditional instructions and unconditional instructions. And in ARM, as opposed to x86, most of the instructions are all conditional, and not just your jumps and those kind of things. Pretty much every instruction is conditional. It's kind of cool. But in the conditional instructions, the subcategories of that are defined by this 2-bit op1 field and another 1-bit op field. If you follow this yellow line kind of over, we can go to one of the subcategories, which is a very common one, which is the data processing and miscellaneous instructions. And you can have other subcategories like data processing with the register, data processing with immediate values, and so on. And those are all further defined by the op1 and op2 fields that you see in green at the top. So if we start to follow that yellow line, we'll look at the register ones. Over here, you have data processing register instructions. And I'm going to kind of go down the line here a little bit. And we see kind of towards the top, there's our move instruction that I had for ASCII text. So that's how I'm going to look at it now. Same information, but I color-coded a little bit. Conditions are blue, registers typically are yellow, all the machine stuff specific to the instruction is red, and our don't care bits are gray. And just to further explain kind of the breakdown of the categories, for our conditional data instructions, they're all going to start with this 00 machine code that you see. And if I were to follow that, now the subcategory, all of these have a 00 and an additional 0. So that's kind of how that breaks apart. And then the extra 4 bits after that down the line define what actual instruction it is, which is pretty cool. It just kind of all makes sense. So another thing, and again, I'm not going to zoom in, it's not really, you don't have to study this code. The point is that it's a small script. Again, before trying to do Hello World, I kind of retrofitted a concept of a tool I wrote a while ago called M to ELF, which is just converting ASCII hex into ELF, like an ELF run executable program. For x86, I had a tool like that interactively. So I wanted to make something like that for ARM. And this is the whole script. It's pretty simple. I mean, it's doing a lot of system calls to bash. This is kind of a example execution of that simple script. Is at the top, you see me typing some binary out by hand, and then I hit enter, and then it tells me that this instruction is move R1, R2. And then below that, I type some binary for what is the same instruction. I just made all those don't care bits ones, and then I noticed that it no longer gets disassembled as a move instruction. It gets disassembled as undefined. That doesn't necessarily mean it's not a move instruction. It's just the disassembler doesn't know what to do with it. But I don't just take its word for it. I want to see what actually happens. So my first test is I start to write an actual assembly program. I start by putting 0 in the R0 register as a point of reference, just to know that it's supposed to be 0 at this point. And then I machine code another move instruction, except for the only difference with this is I'm moving the PC register into R0, and then flipping all the don't care bits to ones to see if the instruction actually does something or errors out. I mean, it looks undefined, but does it still work? That's my first question. So in my GDB debugger, if we look in here, we see the move R0, 0 immediate instruction here, and then we see an undefined instruction below it, and then a NOP after that. And in this view, NOP is showing up as red because it's the next instruction to be executed, meaning at this point in the stage, I've already executed our undefined instruction. So if it didn't do anything, I mean, if it failed, we would have already failed out of this program. If it didn't do anything, then our R0 should still be 0, but if it did do something, then our R0 register should have the PC value, which in this case should be 10060 in this case. So if we look up there, our R0 register has 10060. So it still works. We can screw with those don't care bits. It doesn't matter what we make them. The instructions still work, except for when you disassemble them, they look confusing, which is kind of cool. So in conclusion with that, those bits can be any damn thing. And in this case, you can put whatever you want in there. Or more familiar kinds of things to some of the people here is, whatever you're used to seeing, you can put anything in there. So implications, if I were to run with this concept. Anti-reversing a little bit, because when you statically disassemble, maybe all the instructions look undefined, which is confusing. Steganography, because you can pack anything in there. You can pack information in there as well. Malware signature busting, I mean, if it's just hash-based, it's a quick and dirty way to change the hashes, and maybe better exploit development because you can remove nulls for your shellcode. And that's it. But no, LG, JK. So the point about that is that whole process from noticing that instruction, that move instruction, it was probably after that maybe only 10 to 15 minutes of experimentation. Like, just like 15 minutes, and here I have these theories, and I see sometimes in our community it stops there. Like, you see a cool theory, somebody tries to explain it in a way that, like, arrogantly, that like they've already done it. That's how they're presenting it. Like, they're so cool. The problem is sometimes it doesn't always work out that way. In theory and practice are the same, but in practice they're not. And sometimes you get lucky, but really without proving it, I just think it's lazy. Because, I mean, this is hacking. We have computers. We can test things. To just stop at theory, it doesn't make any sense to me. I mean, my religion is proof of concept or get the fuck out. The proof of concepts have really high currency. And if you don't have it, you don't know. So that's kind of my point with that. Like, I made a lot of bold claims here, but I don't really know necessarily if these things are possible, and really even how trivial it is to implement them. So while this talk has technical parts to it, it's kind of just a sermon delivery content, you know, a little preachy in that way. And it's more just about process, just the process that coming up with a proof of concept, even if it's something as stupid as manipulating don't care bits, the process is hard, and it's worthwhile. So the first thing I tried to experiment with was the question, can I undefine all the instructions? That was kind of the first claim I made. You know, in this screenshot, can they all look undefined like that? And quick answer, cut to the chase, no. About a third to a fourth of the instruction set has don't care bits in it. So you can't do it with all of them. And that took time to figure out. I had to scroll through every single instruction and kind of catalog which ones had don't care bits and which one didn't. So then my first proof of concept, and I called it arm wrestle, is kind of just I guess not really a pun, but a friend, Chapo, he's the one that suggested that name at this point in my playing around. So I wrote a script that would go through, iterate through every single instruction, identify which one it is, and then for the, say like a don't care bit field of like 4 zeros, it would just flip that last 0 to a 1, making it undefined. And it would do that for every single instruction in a binary. So I tested it out on User Games Worm, one of my favorite BSD games packages, the game in that. And I flipped all those bits, and it worked. It didn't segfault. The instructions, when I disassembled it, I had some undefined amounts in there. It was kind of consistent with the amount that I expected to be undefined. And it still works, so that's kind of cool. That first test was pretty successful in the theory that if you can change any bit you want, it works. And now I'm going on some detours here, and I had more questions. Like, that is a theory anecdotally, but really, if I flip any of those don't care bits, could it convert it to a different instruction? And really, no. It became more clear to me when I made the ARM Machinist Atlas, which, as an aside, this is the atlas I'm talking about. I broke down every single instruction in its binary form, so it became visually easier to see things. So no, and the first test I did was I just like mapped out every single instruction in binary, did some fancy regex just to see that stuff didn't overlap. So as a kind of another detour, why are there don't care bits? You know, because you don't really have that in x86. Part of it is because ARM is a very fixed byte instruction set. So you're going to have some bits and some instructions that might not matter. And I think these two instructions illustrate it really well, although they're not all like this. But this is consistent too conceptually with x86. When you compare the subtract and the compare instructions. Subtract, you do a subtraction, but it also has a side effect of setting some flags, like overflowing and carrying and all that. In this case, you know, you're subtracting RM from RN, and you store the result in RD. The result of the subtraction is in the RD register. Well, compare is like subtract. It just isn't supposed to store the result. All it does is set the flags for the side effects, so then you can feed into logic for doing conditional instructions. If you notice, the machine code is very, very similar, if not identical, except for, like, you know, this 4-bit field is 0010 and this one is 1010. It's the difference. And then you'll notice that the S flag is the thing that's supposed to define if you're trying to set the flags or not, because in ARM you can choose whether to set the flags or not. In subtract, it's optional. But in compare, it's not optional. It's hard-coded to a 1. So that's what it's doing. It's definitely always going to be setting the flags. And then we have our don't care bits, which is for the destination register because we're not storing it. So that's kind of how that looks. It looks similar, but being that we don't care about the destination or the output, you can put any 1 or 0 in that field and it won't change what happens to the compare register. What you can do that changes what happens to the compare instruction is if you change the hard coding of that 1 to a 0, which there's no assembly for that because it's too high level, but if you do it in machine code, this is kind of what it looks like. This is the compare instruction, but I have a 0 there instead. And if I compare it in a disassembly, it disassembles as the same thing, but the machine code is slightly different. We have a 5 and then a 4 here instead. And this is me just assembling it out and assembling, linking, running, and it actually is an illegal instruction. It doesn't work because it wouldn't make sense to run a compare without setting doing the thing that it's supposed to do. I'm negating that. So quick little mid presentation demo here. What I'm going to do is do this ARM wrestling. So go ahead and start playing this, and I'll talk us through it. I'm going to do objdump to disassemble, and what I'm disassembling is objdump itself. I'm just looking at the assembly for objdump. So, and I'm going to grab for the .text section, the first 30 lines of that. And what we get here is the assembly. There's no real undefined instructions. This is what it is supposed to look like. So the next thing I do is I run my tool ARMaHYDAN. I'm going to undefine those don't care bits. I'm inputting objdump as the input program, and I'm going to output a program of objdump.wtf, like all the undefined instructions. So it's going to crunch through that, and when it finishes, I'm going to have to then make objdump.wtf executable. So chmod 744 is what I'm going to do, and now it's executable. And now I'm going to run this messed up objdump that has undefined instructions, and I'm going to do -d, and I'm going to run it against itself, and then look for the first few instructions of disassembly. So I have this modified version, this fucked up version of objdump that has all these undefined instructions now that still works, and it's running on itself. It's disassembling itself, and it looks messed up. I just like how meta that is. But so that's a perfect concept for how usually you can undefine all these bits and it doesn't change the functionality, and you get a lot of undefined instructions. So now as a tangent, something that's not as fun as the research I've been doing so far, but still kind of necessary if I want to progress forward. I mentioned that I had a script that kind of profiles through all the instructions and changes them as they go, and I'm smart enough to short-circuit it. If you find that it's such and such instruction, it modifies it and then moves on to the next instruction. It doesn't try to interpret it. Well, is it this instruction? Is it this instruction? And so on. But at this point, I do all the instructions in an alphabetical order, and performance-wise, that's terrible. I really should be doing it in the instructions that are the most common first, for the short-circuiting that profoundly affects the performance by an order of magnitude. However, I don't know what the most common instructions are, and I don't know of any easy list out there that tells that for me. So I have to figure that out for myself. And in this case, I have some screenshots. I mean, this is just me doing alphabetical. This is kind of an order of instructions as they're most common, which this is legitimate. So what I end up having to do is I write a script to profile my entire Raspbian operating system. I go through every single instruction and I count how often they occur. And being that at this point I was using my original Raspberry Pi 1B, it took a while, like days, if not like a week. But I finally get my data and implement it in the script, and it runs a lot faster. But now to be a little bit even more meta, what about including, even though I'm really only trying to modify instructions that have don't care bits, would it make sense to add back instructions that don't have don't care bits? Even though I'm not modifying them, it will help performance-wise for the short-circuiting. Because if it's an instruction that happens the most frequently, whether I'm doing anything with it or not, at least I don't have to check it against all the instructions. I can just be done with it. But then again, if I start adding instructions that don't have don't care bits, that don't happen frequently, that can hurt performance. So I have to do even more benchmarking to see what that sweet spot is. And this actually took even longer to figure out than the first benchmarking. Point is, super, super time consuming, not interesting, but still needs to be done. So I had another side question. As a curious person, I have a lot of questions. And this question I wish I would have got to later, even though it was a necessary question. But at this point, it just confused me, and I got back to it later. But my question was, in the wild, are there actually instructions in real compiled programs that have the don't care bits set to something that's not standard? I know it's a weird question to have, but I want to know. So when I do it, I find something out that surprised me. On average, all instructions have about a 0 to 13% rate of having instructions that have the don't care bits set not to spec to the manual, which is really weird. Like, if you're thinking about it, what compiler is actually going to do, or assembler, or a compiler, what assembler is actually going to do that legitimately, and why? Like, this doesn't make sense. Why is this occurring? And there is an answer for it, but I'll get to that later. But in the back of my head, this is disturbing me a little bit. Other assumptions, because this is an assumption. We make assumptions when all we have is theory without testing it, is these 140 instructions with don't care bits. Can I assume that if I change them, they're all going to show up as undefined? And really quickly, the answer is no, because as I was comparing that subtract and compare instruction, the disassembly, the instructions both showed up as compare. It didn't actually show up as undefined. So now I have to catalog that. Also time consuming. I have to figure out and pinpoint which instructions I can exploit in this way. And it wasn't really that simple. Like some instructions, like this first LD REXD instruction, I had to flip all the ones to zeros. If I just flipped a couple of bits, it would still show up as the correct instruction. So I had to flip all those bits. Some instructions wouldn't like undefined at all, like the compare or the CMN instruction. No matter what one or no matter what zeros it changed to ones, even all of them or some of them, it would never undefine. I'm pointing that phrase. It wouldn't undefine the instruction. So now I have that in the back of my head, which was really demoralizing when I get to an instruction like MRS, because there's numerous don't care bits. I think there's about 11 don't care bits. And really just arbitrarily changing a 0 to a 1 or a 1 to a 0 didn't undefine it. So now I have to exhaustively go through every single iteration, which I think for 11 bits is probably about 2,000 different experimentations, to then arrive at the conclusion that no, I can't undefine it. And I have 140 instructions to check like this. Also time consuming, but I'm thorough. I don't like to stop at just theory. I'm talking mostly about OBJ dump, GDB, maybe radar, as far as disassembling. But obviously the disassembler you're using matters too. So we've been seeing those contexts, but what about IDAPRO? Is that different? And I was working with my friend Average Joe. He had the full version of IDAPRO, so I sent him some samples and checked out what that would look like in IDAPRO. The fascinating thing is you would expect IDAPRO to be a pro at disassembling this stuff, but in practice it works a little bit differently. And I'll zoom in here. In general, it is able to disassemble more instructions. It recognizes more of the bullshit I'm giving it. On the downside, the first instruction it doesn't understand, everything after its data, even valid instructions. So I consider that to be a bit worse with disassembling. So that's kind of cool too. So now I'll move on to the other claims, not just making stuff undefined. That's, in my opinion, that's kind of the most interesting thing. But we'll get to the other things, like randomizing those bits, which in this case, the purpose of it is to change the hashes. You have the same program functionally, size-wise, instruction-wise, but the hashes are all different, and that's kind of cool. It's pretty easy to test. I just retrofitted that same ARM RESTful type script, and instead of flipping one bit, I just flipped all of them there in a random kind of a way. And it worked out perfectly. This is kind of a proof of concept. You have me running the same program each time, but output .1, .2, .3, and I do a MD5 sum of all of them, and they're all different. They all worked. So that's cool. Now we'll get to the claim of steganography. Turns out this is the most complicated thing to pull off, and I think, in my opinion, the dumbest thing. I've talked about steganography here and there in other talks, but if you don't do it really well, steganography is just really stupid. And in this case, it is really stupid and very detectable. But again, I wanted to run with it as an exercise. Obviously I can hide arbitrary bits in there with data. I need to have some metadata to make things more convenient for the user. So I have metadata for how large the file is, so the program itself can know when to stop carving, so you don't have to define that as a user. And kind of a conceptual way of how this works is you have some instructions here, like move and s multiply, sign multiply. That's what it kind of looks like in binary. In red, you have your don't care bits here. And then as a sample assembly program, I'm just alternating move and sign multiply here, like over and over and over. So in binary, this is that whole program. And what I want to pack into it is the phrase POC or GTFO and binary, ASCII. So this is what it looks like, changing those don't care bit fields. This is interspersed 4 bits at a time, the text of POC or GTFO. It doesn't change the functionality of the instructions. In a hex dump, it looks like this. So these are all the changed bytes. And that's the high level of how that's working. It's really not too sophisticated. So does it work? In general, yeah, flawlessly. With that metadata and the data I'm putting in there, I can write a script, inject data in there, and I can use the same script to pull the data out. The data is still valid, still has integrity. However, I realize at this point, I've been doing a lot of hacking around, but I've been neglecting to test run the programs after I finished stegoing them. So I tried that real quick, and damn, it seg faults. So I fucked something up. At this point, I don't know what. I haven't done anything that crazy at this point. And then I remember that question I had a little while ago. There are some instructions in there where the don't care bits are set incorrectly, which I still don't know why. So I decided to kind of investigate that a little bit, hoping that it would answer my question, which it did, to cut to the chase with that. So I got to hack to learn. I got to get to the bottom of it. So I started isolating off some of those off-spec instructions to try to see the context of why they're being run, what instructions are around them, and then correcting the instruction, actually making it to spec to see what would happen. And it's weird. It turned out that when I made the instructions correct, it actually seg faulted that way. Like if I went to a default executable and I changed one of those off-spec instructions to be the correct version of it, that made the program break. Like it was integral that the instruction had to be wrong for the program to work. So what I did is I used Boken because it's a good graphical representation of a disassembly, and it gives really helpful hints. So I found one of those problem instructions, and then I looked for references to that instruction, and I found an instruction that was referencing it, and Boken was helpful enough to give a comment saying it was data. So in this case, I have data in the .text section, which is not necessarily weird or a problem. This happens. You have like jump tables and stuff like that. It's not necessarily data in the sense that like strings are data. These aren't really strings. They might just be memory addresses or something like that that do make sense or belong in a .text section, but they're not instructions. So this kind of makes sense as to why you have data instructions in there that disassemble like instructions, but aren't, and have the don't care bits set differently because, well, they're not real instructions. So that's a difficult problem, and I'm not solving the code versus data problem. It might be solvable, but it's way more complex than what I'm doing right now. So I'm trying to find some clever ways to work around that. So I'm going to do more profiling. I want to see what data instructions are the most common. Like, I already saw what assembly instructions are the most common. Now I'm going to do it for data, because my hope is that maybe, just luckily, some of those false positive data instructions are really, really common, like maybe it's only 1 or 2, and I could just ignore those type of instructions for my stegoing and be done with that problem. Turns out, though, that it wasn't the case. It was fairly evenly distributed. There was like, a top 10 that made up maybe 90% of the instruction set, but I couldn't just ignore instructions outright. I had to handle it in a different way. So my idea was maybe to dynamically blacklist these instructions, like do a first pass of looking at the whole program and seeing which instructions were set incorrectly, and then deciding dynamically to blacklist those instructions, and then even have to record it in the metadata because the program that's extracting it needs to know which instructions to skip as well. You have to communicate that. That's what I end up doing, but then you're thinking, okay, that requires more metadata, and what if you're shoving that metadata into instructions that are actually data, and then you still have the same problem? So how much metadata is that going to take? And also I'm going to put that metadata in the very beginning of my data as to try to reduce the risk even more. And I'm able to get that metadata into 1 byte, like literally doing a dynamic blacklist of the entire instruction set of which instructions I want to skip. I'm recording that down in one byte. And this is my reasoning. Say that the top 3 instructions the false positive is data are like load RD, store RD, and store RH. In this case, this is accurate too. This isn't arbitrary. So if it really is in that order of most common to least common, if I'm profiling and I see STRH show up, I can kind of safely assume that STRD and LDRD are also in that blacklist as well, because they're even more common than STRH. And that's my logic. I only record the most least common one that it actually finds, and just assume that all the other more common statistically instructions are also going to show up there as well. And that's how I get it into 1 byte. In this case, if STRH shows up, I just say the number 3. That's my metadata for it. And that works pretty well. But what happens if that's still not enough? Like, if that data instruction happens to be one of the first instructions, if there's overlap with those top 10 lists. And fortunately, the top 10 for data instructions and the top 10 for actual instructions with don't care bits is almost mutually exclusive. It'd be a lot harder if they weren't, if they're the same. But I'm thinking in theory, it's rare that this could happen, but I really have to get to the bottom of it. I want to prove against that. And it took some research, but I found something that did prove against that. On the Raspbian system, the userbin GA tool, you find here, and I would say, the move instruction for the immediate form is 1 instruction of overlap. Like if you look at the top 10 of both those lists, the move instruction is the only instruction shared. And this move instruction comes in really early on in this binary. So this method still doesn't work. It's a rare edge case, but I still want to solve it. And the convoluted edge case is to just detect the edge case programmatically so I know, so I can adjust accordingly with some other arguments that I have to develop later. There's also false negatives. So like when I'm profiling, I might find a data instruction that just happens to have the don't care bits set correctly. So that's another problem too. It hasn't come up in practice, but that's another issue. So my solution to kind of both those past problems is to have a blacklist override. Like I can actually manually override that blacklist and set it to a higher threshold. So if you stego and it's segfault, so you can make that blacklist more aggressive, and it won't segfault anymore because you're skipping over the correct instructions. It's just now you're going to have less data space to encode data into. And then an edge case of an edge case. We can sometimes hit a point where we're blacklisting so many instructions that we still segfault. So I don't have a fix for that. It's a small edge case, but it happens. So in this case, all I can say is, if you run the tool, you still get a segfault. I guess you can't stego that program. At least it's a small problem though. And then finally, this is noisy. If you were to look at a binary and have the question, well, did somebody stego this program in this method? Well, you have a point of reference on what the instructions are supposed to be looking like. So if it was stegoed, all these bits are going to be changed. So you can with some confidence say this program's been messed with. It's not the original program. Maybe it is stegoed. So in this context, this is why I said steganography is stupid. There's a lot of heuristics I can do. I mean, I can't just definitely say if these don't care bits are off spec, then this is definitely stego. I can't say that because there is a range of instructions that are going to be data that will throw that off. But if the program has been stegoed, it will most likely be significantly higher than that 13% rate. Like really, just by random luck, only about 1 in 16 of the don't care bit fields are going to be normal looking for instructions that only have 4 bits of don't care bits. But yeah, the rate will be even higher than that. So we can look at that as a profile, although I would say as another edge case, libraries tend to have way more than that 13%, so you gotta kind of keep that in mind as well. But there's other things, like I am recording metadata, so if I stego the program, the metadata will be larger than 0, obviously. And fortunately, don't care bits are typically zeros in a lot of the instructions. So if you do see 0 as your metadata, then it probably wasn't stegoed. You can kind of correlate this information. Also, if the metadata isn't 0, like it's non-zero, but it would seem to indicate that the amount of data is larger than the program you're even looking at, well then these are just random 1s and 0s for you don't care bits that couldn't mean it's stego, because you can't pack more data into less data. And then, our blacklist information, we can correlate that too. We can actually look to see how much instructions we should be blacklisting and compare it to our actual blacklist in the metadata, and we can assume whether or not it really matches or combines in that way in a couple of different contexts. Also, the very last thing, which I'm not going to cover too much for reasons, the shellcode part. So I can say with confidence that you can use this method to remove nulls completely out of some instructions. On the side here, I have, in the middle section here, we have all these instructions. This is the full list of instructions you can do this with. Other instructions you can't. So we have the machine code on the side here. All these yellow highlighted nulls are the nulls that would be there. This is where you're going to have at least a don't care nibble. So I put the corresponding bits, and on the right side here, they no longer have nulls. So in theory, this does work. In practice, I'm not going to say shit. I'm not an exploit developer. I haven't tested it, and I think it's irresponsible to say that this is going to help your exploitation, especially since really, if you look into it, thumb instructions, being that they're a little bit more compactly encoded and they're 16-bit, they tend to usually not have null bytes in them, and for the ones that do, you can do a little bit of self-modifying code to edge those out. But again, this isn't my thing, so I'm not going to actually boldly claim that this is going to help you with exploitation, because that's lazy if I'm not actually testing it. And finally, let's go ahead and look at a proof of concept of ARMaHYDAN pulling stego information out of some executables. And by the way, I called it ARMaHYDAN because it's ARM, but HYDAN was a tool, I think it was written about like a decade ago. It was a steganography tool written for x86. Kind of similar concept, like say, like some instructions, like say XOR. There's more than one way to do like XOR EAX, or well, that's actually not, or that's exchange. But anyway, you can encode it in a couple of different ways that are both valid, and compilers only do one way, but if you were to do alternating ways in your binary, you can kind of encode data that way, and that's kind of one of the heuristics that they use to do that. So I mean, my implementation is a lot different, but the concept is very similar. So that's why I call this ARMaHYDAN. So let's go ahead and look through this POC here. So I'm listing what I have in this directory. I have a file called ARM POC. I'm running a file on it to see what it is. It looks like an alpha executable. Cool, so I'm gonna make it executable. I'm gonna run it to see what it does. And it does something. It's kind of dumping like a quick help file. So it's a bccmd, apparently. That's what this instruction is. Okay, cool. So now I'm actually comparing this ARM POC with the actual bccmd, and I see it's the same file size, but if we check the hashes against each other, the quick and dirty steg analysis, we see the hashes are different. It's cool. So we're going to run ARMaHYDAN against it. We're going to extract from ARM POC. Our output is going to be to mystery.out. So we run that just to see what data we can pull out of this command. And we run a file on the output, and this is also a program. So we packed a program inside of a program. That's kind of cool. So we make it executable, and it just says Linux. So we compare a uname, okay, Linux. Let's go ahead and compare the file sizes of mystery out to uname and same file sizes. Cool, right? It worked. Let's compare the hashes of that just in case, so let's see what happens. So we're typing that out. Our extracted uname to real uname, the hashes are different. So shit, inception. We extract out of that mystery.out and output that to mystery2.out and run file against that and see it's a text file. So if we cat it, CactusCon. So that, I think that's really cool. You can, on multiple layers, pack the data in. And that's a quick proof of concept for ARMaHYDAN, which I have on GitHub. On the last slide, I'll show the link to that. So in conclusion, regardless of what this talk was about, what the ARMaHYDAN tool and messing with don't care bits and ARM and all that, theories are quick and sexy. It's easy. Like, to do all this work, it took a lot of testing. It took a lot of profiling, half of which had nothing to do with the progression of my script, maybe its performance or answering some questions, but those were really important and crucial as well. That took me like 4 to 5 months. But to come up with a theory took me 15 minutes. So I kind of want to give a perspective on the difference there. The process just takes a lot of work, a lot of time, and it's not really that sexy. I mean, the majority of this talk might have actually legitimately been boring, but that's an important point. I'm just saying it's crucial to do it. Like, there are theoretical fields that exist, and that's okay. This isn't one of them. We shouldn't just talk about theory, we should do it. So really, the sermon is, if you don't have a POC, like, get the fuck out. And I have a little quote up here. I'll zoom into it. But sometimes we have friends that say things like this, and it's just really, really cringy. Like, I'm not saying they can't do this, but shut up until you do it. And this is the actual end of the talk. Not a lot of people, but if you have any questions, go for it. Yeah, Joe. Of course.
Can your decoding be done dynamically? Does it have to be run? Can it just be scripted out?
You mean like on like batching well, okay. He's asking if it can be scripted out. Are you talking about like batching a bunch of executables, or?
Yeah, if I want to pack a bunch of stuff inside, I mean, am I limited on what I can pack inside? Could it be a program? Could it be shellcode? Does it have to be a particular format?
In this case, as it stands now, and it's good that it's open source, but it is limited to an ELF executable because I am doing some pre-processing first to, it won't actually run if it sees that it's not an ELF executable. It actually does look specifically for the .text section and only applies its logic to that, because obviously if it's like considering the data section as instructions, it's going to fuck it up. So I do have to be very careful about that. However, that's just referring to this tool. It doesn't mean that you couldn't apply the same process to shellcode. It's just this tool as it stands doesn't do that. But of course, with shellcode, you could change those don't care bits to anything you want, and it would work the same as this. But no, my tool doesn't do that. It doesn't do batching by default, but it is a command with arguments, and it's not an interactive program. So you could probably write a one-liner that does that. It should work.
Come on, man. POC or GTFO?
Yeah. One other thing, I described a lot of different ways as profiling and researching that were all time-consuming. I didn't literally tell you all of the things, so it was even more time-consuming than I'm giving away, because I had other random questions that don't apply to this. But I did have the question, how many don't care bits in ELF executables? How many don't care bits total are there on the entire Raspbian system? I asked that question, and I profiled it, and I think this was when I didn't have my Raspberry Pi 3 B+. So it took a while, maybe 2 weeks, to find the answer to this question, and it was something in the order of like 500 megabytes. That's really cool. That's like free data, you know? I mean, it's easier said than done because if you really wanted to like store a lot of data and all that, you'd have to add more complexity because you're going to be splitting that data across several executables. You got to track that. But you know, it's kind of interesting too. As far as like batching, like another kind of application of that if you wanted to do that. But in practice, I don't know, so I wouldn't really say it works or I've done it. Are there any other questions? Just Joe, that sounds like a normal talk for me. All right, thank you.